Molecular orbital theory is the most advanced bonding theory that we'll cover in general chemistry. As with many things in science, the origins of the theory stem from an observation. That observation was that liquid oxygen sticks to a magnet. From our previous look at electron configurations, we know that in order to stick to a magnet or become influenced by a magnetic field, a molecule or an atom must have unpaired electrons. When we look at the Lewis structure of oxygen, we do not see any unpaired electrons. We see 2 pairs of bonding electrons and 4 lone pairs in the molecule, but we don't see any unpaired electrons. So we'll be able to answer that question about why oxygen sticks to a magnet by taking a look at molecular orbital theory. Before we get into molecular orbital theory, recall that waves have 2 ways that they can interact. They can interact either in constructive interference or in destructive interference. In the case of constructive interference, the waves overlap peak to peak, trough to trough, and mathematically they add together. So you get a higher peak and a lower trough. So you increase the amplitude of the wave that is formed when 2 waves overlap in phase. With destructive interference, when the waves overlap, it's peak to trough and trough to peak. And so mathematically, these waves add together to make nothing. The mathematical sum of the wave is essentially 0. And so that is called destructive interference. Because we know that electrons can behave as waves, we also know that when electrons can overlap, in other words, when orbitals can overlap with other orbitals of other atoms, they can either do so in a way that causes the orbitals to be in phase or out of phase. And in this example, you can see that we have a plus sign on this s orbital and a plus sign on that s orbital. And so if these 2 waves, these 2 electrons were to overlap, that would form a constructive interference. That would be a bond. Down here we can see that we have a plus sign on the orbital and a negative sign on that orbital, and that would indicate that the orbitals are out of phase. And so when these 2 orbitals overlap, we do not get a bond. So the simplest case that we can look at is that of hydrogen, which is just the H2 molecule. Molecular orbital theory states that when the s orbitals of 2 hydrogen atoms overlap, we can either get overlap in phase or overlap that is out of phase. And in the case that is represented on this energy diagram by a lower energy orbital. In this case we call this a molecular orbital, sometimes just called MO. And these over here would be the atomic orbitals from which they are derived. And the y-axis here is going to be energy. So this is an energy diagram. Notice that there are 2 molecular orbitals. One molecular orbital is higher in energy and one molecular orbital is lower in energy. The one that is higher in energy comes from the out of phase overlap. The one that is lower in energy comes from the in phase overlap. So to review, there are 2 possibilities when the s orbitals of 2 hydrogen atoms overlap. The 2 possibilities are that they overlap in phase, in which case you get an atomic orbital that is lower in energy. The other option is that you get out of phase overlap, and that gives an atomic orbital that is higher in energy. So the first thing we want to do is put the valence electrons in the appropriate atomic orbitals. In this case, hydrogen has a 1s1 electron configuration, so we're just going to place 1 electron in each of the atomic orbitals. From here, the rules that you learned for placing electrons into orbitals are exactly the same. We're going to place electrons in the lowest energy levels first and then work our way up. In this case, we only have 2 electrons, and so both of those electrons are going to go in the lowest molecular orbital. Okay, let's look at another one. Let's look at H2 minus. In this case, we've got 2 electrons from one of the hydrogens. It doesn't make any difference which one, so we'll call this one having a 1s2 electron configuration, and this one as a 1s1 electron configuration. Because we have this minus sign right here, it indicates that we have an extra electron. And so what we're going to do is we're going to place 1 electron into the atomic orbital, spin up, and 1 spin down on the left, and we're going to place 1 spin up on the right. And so what that does is it gives us 3 electrons that we have to place into the molecular orbitals. And in this case, we're going to have to put electrons here. So we put 1, 2. We have 1 left. So it's going to have to go into the antibonding molecular orbital. So to round out this set of examples, I want to look at the dihelium, or the He2 molecule. And I want to explain why there is no bonding in this molecule. If you look at the electron configurations of helium atoms, you notice that it has a 1s2, each one does, electron configuration. And so that is 2 electrons in the s orbital of each helium atom. So in the atomic orbitals, we're going to place 2 electrons in each. And so that gives us a total of 4 electrons that we're going to have to place into the appropriate atomic or molecular orbitals. So to do that, we're going to start with the lowest energy molecular orbital. We're going to put 2 electrons there. And then we're going to move up to the next highest molecular orbital, and we'll place the remaining 2 electrons there. And so one thing to note is that on this scale of energy here, the amount of energy between, that is the difference between the antibonding and the bonding molecular orbitals, is the same. And so whenever 2 orbitals overlap to give us a bonding molecular orbital, we are going to have a release of energy because the energy is going to be lower. And whenever atomic orbitals overlap to give us a antibonding molecular orbital, that's going to cost us energy. And so in this example, the energy that we get back is going to be from this bonding molecular orbital, and the energy that it costs us is going to be from this antibonding molecular orbital. So since those energies are the same, they essentially cancel out, and we get no bonding in this molecule. So a brief word about terminology. We have this molecular orbital down here. A lot of times that one's just called a sigma, but it's a bonding molecular orbital. This molecular orbital up here, we call it a sigma star, and that is the antibonding molecular orbital.